Alright, so today we're going to look back at the examples that you were supposed to work on your own, just to kind of give you an idea of how this is going to work. Again, we're going to come in and we try to identify what's going to be our inside of a function for which there is a derivative on the outside. So as you can see here, you should have kind of decided to let your u equal x cubed plus 1. Then your derivative of u would be 3x squared dx. And so I can see that I have an x squared out here. So, and the 5 is a rider, so I'm going to pull the rider constant out. I'm going to need to get my x squared, I need a 3, so I'm going to put in a 3 and take out a 3 for a correction. And then we're going to continue with the rest of the problem. Tangent of our x cubed plus 1 dx. I'm using that pattern recognition. I'm deciding that the box that I'm going to pack all the stuff back in is really the tangent of u. So I can pack all of it back in. So I'm going to end up with 5/3. Pack all the outside stuff back in. That becomes your du. And then I am looking at an integration of the form the antiderivative of tangent of u. Now, of course, this is where you should have memorized from the previous examples over here that our rule for integrating tangent is going to be negative natural log cosine of u plus c with the absolute value on it. So negative natural log, so negative 5/3, bring your constant, natural log absolute value cosine of u, which is going to be x cubed plus 1, and then of course plus your c. So at this point you do your u substitution, you reveal what rule you're integrating under, which is a tangent of u integration, and then hopefully you've memorized the rule that we discovered last time. Alright, let's take a look at this one. Again, practicing with this. I would look at this and decide that I would probably make my inside of the function be this e to the negative x. And so I'm going to let my u equal e to the negative x. That makes my du, remember the derivative of an exponential is itself times the derivative of the exponent, which is going to be negative 1. And then of course dx. And so as I look at what I have up here to integrate, this 2 is going to be a rider, so I'm going to pull it out and let it ride along. My e to the negative x is missing the negative, so that's just a constant so that we can put in a correction. I put in the negative, I take out the negative. Maybe I'll put parentheses to show that I'm multiplying by that. And then what I'm going to do is reveal the form. So I take the negative 2 in front, integrate, I pack all of the stuff back in the box. Our box in this case is going to be the secant of u. So I pack all the derivatives on the outside from the chain rule process back in. So I have secant of u, and then these two go together to make du. So now I have to integrate the trig integration rule for secant. And if we again look back on the previous page from where we did this the last time, and again we don't want to recreate this process every time, so that's why when we are doing the antiderivative of a secant, that we just remember that the antiderivative of secant is going to be natural log secant of x plus tangent of x plus c. So natural log absolute value, bring your negative 2, natural log absolute value secant of u plus tangent of u, and then plus c. Okay, so that kind of shows you some of the applications using those ones that we developed. Now I probably should, let's go ahead and show the work for getting this last one right here. I had told you to do part D on your own. So let's add this in as an example just to make sure we're thorough in all of our notes. So we're trying to integrate cosecant of x dx, which is not one of the rules that we know. So our initial thought, using the long way like we did here, over on this one we multiplied by a form of 1. And I'm going to do the same thing here. I'm going to multiply by a form of 1. And the form of 1 I'm going to multiply by is going to be cosecant of x plus cotangent of x, because that's going to give me something that has known derivatives in it. So cosecant of x plus cotangent of x dx. So I multiply by a form of 1. When I do that, I'm going to end up with cosecant squared x plus cosecant x cotangent x all over my cosecant x plus cotangent x dx. And so just like we did before, I'm going to utilize that log rule, and I'm going to let my u, actually let me put that in, I like to do the u substitution if I'm showing it the inside by making that the denominator. So I'm going to let u equal cosecant x plus cotangent x. Then its derivative, the derivative of cosecant, is going to be cosecant cotangent. Your derivative of cotangent is cosecant squared. Now these have negatives in front of them, so we won't forget those. So minus your cotangent, or your cosecant squared, dx. And then we see that what we're basically missing here from up here is a negative. So we're going to add in a correction. I'll just stick it on the front and then put your corrector on the outside. So our integration is going to be of the form negative antiderivative of this entire top is now your du over u, which is going to be negative natural log absolute value of u plus c, and then we finish it off by getting negative natural log of cosecant of x plus cotangent of x plus c. And like I said, you're never going to, for these rules, I would never recreate them from scratch. Just memorize them and add them to your, basically your integration rules for all the trig functions. A little bit harder to memorize, but really not too terrible bad if you think about how it works. Okay, now let's take a look at example 12 and working through those. In example A, this is clearly going to be a log rule problem. If I let u equal x squared minus 4, my du would be 2x dx. I see that I am missing a constant of 2 up here, so I add it in and I put in a corrector. So we end up with 1/2 integral of du over u, which is going to give me 1/2 natural log absolute value of u plus c, which then gets me putting it back in terms of x, natural log of x squared minus 4 absolute value plus c. So this is a very straightforward log rule integration. Now take a look at B. Now B, you're trying to look for a way to manipulate this, and kind of when we're doing the log rule in section 5.7, most of the time you're looking to make your u substitution the denominator. What we want to do with this one is I'm going to kind of take this x and just put it up in the top so that I only have the natural log of x in the denominator, because our idea in section 5.7 is that when you do your u substitution, you let your u equal the denominator. Well, since if I let u equal natural log of x, then my du is 1 over x dx. And so you can see why I moved the x from the denominator up. I'm trying to make sure that my derivative of u is in the numerator so that I can get this in the correct form. Now the 5 in this problem is actually a writer, so I'm going to pull that out, and then I would have my 1 over x over natural log of x dx, and now I can see that we have it in the form natural log of du over u, that I can make that u substitution for the natural log, and this is my du. So now I can integrate it. The antiderivative of 1 over u du is natural log of absolute value of u. My u is natural log of x. and then of course plus c. So we add that back in. All right, now taking a look at this one. This one is an example of where it's going to be a u substitution, and I am going to let u equal natural log of x, but it's not going to end up being a log rule for the antiderivative. Let's take a look at what happens here. If I rewrite this, this is going to be the integral, and I'm going to change this to natural log of x to the 2/3 over 4x, and then my dx. And what you want to recognize on this one is that what I'm going to do is I am going to let u equal the inside natural log of x. And if I do that as my u substitution, my du is going to be 1 over x dx. So this dividing by x part here is actually part of the derivative of my inside function. I'm going to pull the 4 out because there's no 4 here, so that must be a writer, so I pull it out. And then I'm going to rewrite this as natural log of x to the 2/3 and then 1 over x dx. And if I do that, hopefully you can see that what we're doing, the box that we're packing everything back into, my box is actually a power function. It's u to the 2/3. So it's u to the 2/3 du. So this one is a power rule, not a log rule problem. So in both of these cases, you were trying to look for targeting where the u was going to be the denominator to get it in the log rule form. And I let u equal the denominator. I did a little playing around with it to move the x up, but I made u the denominator and I got it into the log rule form. But because this one, when you kind of rewrite it in this fashion, you sort of see that you have a ln of x to a power that my inside function is the ln of x. It wouldn't help me to make u equal to 4x because its derivative is 4 and I don't have any logs in there at all. So hopefully you can see the difference that this is a power rule problem. And our final answer for this one would be 1/4. Put your u back in, natural log of x to the 2/3. Oh, antiderivative, add 1, so that would be, if I add 1 to my power, I would end up at 5/3. And then remember you have to divide by 5/3, which is multiplying by 3/5, so it ends up being 3/20. And then of course our plus c. So that's how we would work part C, and we had to recognize that that was a power rule. Alright, I'm just going to change color so it's a little bit easier to tell that I'm on, let's do purple, I'm on this one. Now again in this one, I'm going to let my u equal natural log of x, just like I did over here. When I do that, my du is going to be 1 over x dx. So when I rewrite this one into kind of a nicer form to see what's going on, I'm going to have the cosecant of natural log of x. Then I'm going to have this 1 over x dx, and then hopefully this e you'll recognize as a constant. I'm going to pull that out as a writer. So I'm kind of just reordering this. And so when I go to do my antiderivative, the form, the box that I am looking at to pack everything back up is really the cosecant of u. So I pack all the derivatives that are on the outside back in. So I'm really integrating cosecant of u du, because this is my du. And then at this point we have to remember what is the antiderivative of cosecant, that's one of the new ones that we learned. And if you want, we can flip back to the page, scan down here to the bottom where I just did that. The antiderivative of cosecant is a negative natural log, absolute value, cosecant plus cotangent plus c. So we have, let's see, try to fit that in there. I'm actually just going to come down here. So that would equal 1 over e, natural log, absolute value, cosecant u plus cotangent u, absolute value, plus c. Okay. So hopefully you can start to see kind of how the trick is of working with some of these log rule problems. Let's do one last one. We're going to look at our example D. Let me just fix that. I'm going to, since I'm going to move up and do this one above it, so that way I have a little bit of room to work with. And I'll just change color here. So I'm going to kind of come right here. Now, again, when you look at this one, I'm going to go back to, once I recognize that the derivative of arctangent is 1 over 1 plus x squared. You have to kind of reveal where the derivative is. So I'm going to rewrite this as arctangent of x and then 1 over 1 plus x squared dx. So when I go to choose a u here, I'm going to let u equal the arctangent of x. My du is going to be 1 over 1 plus x squared dx. And so really what I'm integrating here, as complicated as it looks, is really, because you're packing things back into your box, that really what I'm looking at for the box is just u. Everything gets packed back in. I'm integrating u du. So this is a power rule problem. And so with the power rule problem, and when I go to integrate it, it's going to be u squared divided by 2, or 1/2 u squared. So 1/2, I'm going to write it as inverse tangent of x because that's shorter, plus squared plus c. And so that would be my answer for part D. So all of these here are really just practicing different things that you might see if you had the log rule. Now, kind of before I do example 13, I'm going to insert a page. I'm just going to do a blank page here because there's a couple of examples that I want to do. Mostly because in this set of notes I didn't have a lot of these examples. And in section 5.5, when we are doing this u substitution and chain rule, I want to specifically talk about u substitution with exponential functions. Because I think it might kind of be interesting or in your best interest to kind of talk about this to see how we work backwards and find antiderivatives of exponential functions. All right, now let's remind ourselves from 5.1 when we were doing basic antiderivatives that if I wanted to integrate e to the x dx, well, since the derivative of e to the x is e to the x, the antiderivative of e to the x is e to the x plus c. So that one's fairly straightforward. Now where it started to get interesting was where we were doing our, because the derivative of e to the x plus c with respect to x is e to the x. All right. What's more interesting is the ones where your base is not e. So what if I wanted to find the antiderivative of, say, 2 to the x or b to the x dx instead of our antiderivative of e to the x? Well, let's remind ourselves, let's recall from our chapter 3 that if I was going to take the derivative of b to the x with respect to x, the derivative of b to the x with respect to x is we would take our exponential function, the derivative of an exponential is itself, times, remember we had an additional constant that was the natural log of the base. So when I take the derivative, I have itself times the natural log of the base. So if I'm working backwards, I would have itself and then I have to divide by the natural log of the base. Because remember, you're doing a reverse process, plus c. Now, so why does this work out? Just to kind of verify to you, if I were to take the derivative of b to the x over natural log of b plus c with respect to x, 1 over natural log of b is a constant. So the derivative of a constant times a function is the constant times the derivative of the function. The derivative of b to the x is b to the x times natural log of b, and the derivative of the constant is 0. And you see that those would cancel out, and I would end up back at b to the x. Okay, so that's from 5.1, knowing what your exponential rules are for integration. So that's the working backwards. So now that we have those, let's talk about what would happen if you had to do a u substitution with an exponential. All right, so for example, let's say example 1 here. Suppose I wanted to integrate 5 to the 3x dx. Okay, now what you would recognize here is that this is going to have to be a U substitution problem, because when I look at this, I have an inside function. When you're doing exponentials, your inside function is the exponent. So we're kind of assuming that there are parentheses here. And so the idea is that what I'm going to let my u equal is the exponent. That makes my du equal to 3 dx. And so what I'm essentially doing here is I'm missing the constant 3 out of my derivative. So I'm going to add that in. So when I go to integrate, here's my 5 to the u, and then I need a 3 to have the du to put back in, my correction on that. So I'm going to add the 3 in, make it times, and then I'm going to pull it out over here. So now the form that I am integrating, the box that I'm packing things back up into, is the 5 to the u. So what I'm really integrating is 1/3 the indefinite integral or antiderivative of 5 to the u du. Now I use my antiderivative rule for exponentials. So I would need to do the antiderivative of 5 to the u is itself divided by, okay, that's my rule up here, divided by the natural log of the base, which is 5, plus c, and then I convert it from u back to x, 1/3 or 1/3 natural log of 5, we might as well put those together, times my 5 to the 3x, and then plus c. So that's kind of the idea of what we're looking for with the exponential functions. All right, let's look at another example. Example 2. Suppose I had to integrate, let's do 1/3 to the, let's do 3x squared, and let's assume that we have a 5x out here, dx. All right, so let's take a look at this example. Again, the idea here is that you're going to have to recognize that the inside of your function is the exponent, that this is exponential. So the base is 1/3, the inside of the function, where I'm plugging stuff in, is going to be the exponent. So you need to let your u equal 3x squared. Your du would be 6x dx. So when I take a look at this problem, that 5 out here is a writer, so I'm going to pull that out. And then I have my x. And if you want to, sometimes students like to take the outside stuff you're going to pack back up and put it together. So you could write your function 1/3 to the 3x squared. That's going to be my 1/3 to the u. And then I'm going to put the x with the dx, and then I'm missing a 6. So I add the 6 in, and I correct for the fact that I added the 6 in. The box that this is going to get packed back up in is this. So it's 1/3 to the u. So I'm really doing 5/6 antiderivative of 1/3 to the u du. Now I apply my exponential integration rule. So I have my 5/6 constant, bring it along. The antiderivative of an exponential is itself 1/3 to the u divided by the natural log of the base, 1/3, plus c, and then just putting all your constants together, 5/6 natural log of 1/3 times my 1/3 to the u, which was 3x squared, plus c. All right, so that gives you a few examples of how to deal with some of these exponential functions that you're looking at. Now, and I really just wanted to do that because I realized that this set of notes did not have those examples in it. And in section 5.5, your U substitutions that you're working with, after I substitute the U in, I will either end up with a power rule integration, a trig rule integration, or an exponential rule integration. So those are essentially what you're looking at in section 5.5, that after I make the substitution, that I am going to end up with some nice functions that I know how to integrate. Either it's a power function where you add 1 to the power and divide, a trig rule where if it's sine, you know its antiderivative is negative cosine. If it is tangent squared, you know that its antiderivative must have been, the antiderivative of tangent squared is, all of a sudden my mind went blank as I was doing these. The antiderivative of tangent squared is not one you know. The antiderivative of secant squared is your tangent. Okay, so you see how you get confused on these. So you want to take a look, make sure you know these rules, and then the u substitutions in section 5.5 will work back to those. Now the u substitutions that you're doing in section 5.7 are always going to lead to, after you do the u substitution, it's going to lead to a log rule that you're going to be using. And so that's kind of the difference. In 5.5, 5.7, and 5.8, we are using u substitution. That's our technique. They just group together after I do the u substitution. The rule that I use to integrate is different in the sections. And just to be thorough while I'm here, section 5.8, you do a u substitution, and after you do the u substitution, it's going to end up being a inverse trig rule. So technically that's kind of why I put all 3 of these in the same set of class notes, is because you're doing u substitution in all of them. They're just each looking at different rules after you do the u substitution. All right, one last thing before I leave this set of little video behind is I also want to talk about example 13, just to kind of get you started on the idea of what do I do if I have a definite integral and I need to do a u substitution in order to do the problem. Now I have a whole video where it's going to talk about this in more detail coming up. So I'm just going to do this one just to kind of show you intuitively you should know what you're doing. That if I want to calculate a definite integral, remember that we are doing the net change. So we're using our fundamental theorem of calculus. I need to find an antiderivative. So I'm going to call this little f of x. That I am going to find, step 1, find an antiderivative of little f of x, which we call big F of x. Okay, and we don't worry about the constant because we're doing a definite integral, so we're going to be calculating our net change, and according to the fundamental theorem of calculus, we plug in b and then we plug in a and we calculate our net change. So our final answer when we are doing a definite integral, we recognize that we will end up with a number, not a antiderivative function. We're going to end up with a number. However, the process is very much related in that we are still going to find the antiderivative first by doing a u substitution. I'm going to let u equal x squared plus 1, and my du then would be 2x dx. So I see that I'm missing a 2, so I do the same thing we did before. I put in my correction and I add the 2 in. Now here's where a little bit of the difference comes in. If I'm going to change this over to my u's, I'm going to pack it back up into the box. We recognize that our box is going to be u cubed. So I pack it back in, so I have u cubed, and the stuff that gets packed back in becomes du. Now notice that there's one very thing that you have to be careful of here. I'm doing a definite integral. A definite integral starts as a definite integral and it has to stay a definite integral. So I can't leave off the bounds here. I have to actually put the bounds back in. Now what we'll see here though is don't just write 0 and 1 here. We just switched everything over to be in terms of u, so I need to switch my bounds as well. So I need to switch bounds, and I'm basically saying when x is equal to 0 over here, using this rule, my u is going to be 0 squared plus 1 or 1. So that's what gets filled in for your lower bound. And when x is equal to 1, my u is going to be 1 squared plus 1 or 2, and that's what gets filled in here. Now the nice thing about definite integrals is when I actually now do the integration, I add 1 to my power and then divide by the 4 or multiply by 1/4. I show that I'm doing a definite integral by evaluating this at 1 to 2. Now notice that these are still u's, and it's still a u here. Now I could switch back to x's and switch my bounds back to x's, but you actually don't need to. I'm in u's and these are u's, so I'm just going to go ahead and calculate my net change. So I would have 1/8, plug in your 2 to the 4th, minus your 1/8, and then your 1 to the 4th. That this is my f of b minus f of a, except this was the b in terms of u. And so was my a. And it doesn't matter whether you're in terms of x or in terms of u, as long as you switch your bounds, you're fine. And so your final answer is going to be whatever 2 to the 4th is 2 cubed is 8, 2 to the 4th is 16, 16 divided by 8 is 2, minus 1/8, or 1 7/8 would be our final answer. Now notice that if I were to do this problem and put it back in the x's, so this is kind of our alternate, maybe I do pattern recognition. Maybe I never actually substitute the u in. Maybe when I get to here, I just realize I pack everything back up in, and I'm going to take the antiderivative of u cubed, and in my head, I just go ahead and just do the problem. Sometimes when you're doing these, if you can see that and you don't actually have to write this u step down, I could just integrate it and think, well, u cubed, the antiderivative would be u to the 4th, and then divided by the 4 plus c, but remember, don't do plus c because we're doing a definite integral. And then when I put my bounds on, because I was ignoring the u, I used it to start the problem, but I'm still in terms of x, I would do this from 0 to 1. Now notice when I go to calculate the net change, it would be 1/8. Plug 1 in. 1 squared plus 1 is 2. Oh, I get 2 to the 4th. That's the same thing I got up here. Minus my 1/8. I plug in 0 for x, and I'm going to get 1/8 times 0 plus 1 to the 4th. And you see you get the exact same answer whether I switch it to u or I stay in x. So you're going to have an option of 2 methods when you do definite integrals. But the one rule to remember, the main idea here is that if you start with a definite integral, it better be a definite integral in every step that you write down, whether you switch to u's or you stay with the x bounds when you're doing it. So you want to be careful about that. And there will be another set of notes and examples to do several more of these, but that should be enough to get you started on any that you have in your homework.